Okay, so this is exam 2. I'm going to work version B, and I'm just going to take a few minutes to demonstrate how to solve these problems. It's very important that you understand how to work these problems because you're going to see them again if you take a retake exam the last week of April, and as well if on your final exam. It's cumulative. So let's just start with number 1. What is the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th? Now it gives you a frequency, so that's new. And so you just define that as, and it's in seconds. So 4.62 times 10 to the 14th reciprocal seconds. And it wants the wavelength, so this is C equals lambda nu, and that is the formula you know, and you should see on your periodic table that C equals 2.9979 times 10 to the 8th meters per second. So now you solve for wavelength, which is what the question's asking for, so lambda equals C divided by nu. And then you come over here and you do the plug and chug. So you're going to say that the lambda, the wavelength, is 2.9979 times 10 to the 8th meters per second. And then you divide that by 4.62 times 10 to the 14th reciprocal centimeters. And that's going to work out to be 0.000000649 meters. And this is one of the reasons why I told you to get a calculator for $10, one of these TI 3034s that you can use on the exams, because these calculators are different when regards to using the exponents. And so you don't want to have to use one of my borrowed calculators if this is the first time you're working this problem, because you use the graphing calculators to practice these. Now, we need this in nanometers, so then to convert from meters to nanometers, you just do the metric system dimensional analysis, and for 1 meter you have 9 zeros of nanometers, and that works out to be 649 nanometers, and that answer is D. Okay, now let's go on to problem, and see this is B, so if you have the other version, you can just see how to solve these. Which of the following is a weak electrolyte? All right, so let's review the definition of weak electrolyte. A weak electrolyte is one that partially dissociates into its ions, so into its plus and minuses in aqueous solutions, and therefore would barely light up a light bulb, right? So your strong electrolytes will be the compounds that are metals with nonmetals. And these metals with nonmetals are like lithium chloride, so that would be a strong one. Ammonium hydroxide, that would be a strong one. Let me not circle that so you don't think. Because you know to name that, you got to go ammonium hydroxide. Okay, so that breaks up into ions. This one, anytime you have your carbons, hydrogens, and oxygens, those are your carbohydrates. Those are nonmetals with nonmetals. Those are organic compounds. And you should have known that those are non-electrolytes. A lot of people chose that. It's not a weak electrolyte. It's a non. It's not. Here you have magnesium nitrate, and that breaks up into 2 magnesium and 3 nitrates. Okay, so you know that that's a strong one. So the only one that is a weak is HF. Well, you should have seen that the H is in the beginning, so you should say, okay, that's an acid, and it's not one of the 7 memorized strong acids. And I say memorized. I told you to memorize the 7 strong acids. Okay, so you should know what the 7 strong acids are. The students that missed this, and a lot of students did, it's because you still haven't learned how to name your compounds. Chapter 2, you still have issues with assigning positives and minuses for polyatomic anions. You still don't know that magnesium breaks up into Mg2 plus ions because it's group 2 and it's a metal, so it's going to be a cation. So this is going to come back to haunt you every exam because these principles build upon your knowledge of understanding how to make these compounds. So go back to chapter 2 and learn these concepts. Okay, question number 3. This was a new concept. Most people did really well on the new concepts. Quantum numbers. You know the quantum numbers are N, L, M sub L, and M sub S. And so N is kind of the row number. And then, so if you have, you can look at the periodic table and you can see that A is one that cannot exist because if you have row number 1, so if N equals 1, L would have to only be 0 because it can't go all the way up to 1. And L is the shape, which is the S shape. Okay, so then you go into the orbitals of N equals 2. Well, if N equals 2, you can have L equals 0 and L equals 1. That's S shape and P shape. And you can actually go to the second row of the periodic table and you'll see that you have the S block and the P block. So there's no, to get 2, you have to have N equals 3. So N equals 3 is the third row, and there you can have L of S shape, L of 1, which is P shape, or L of 2, which is D shape. So that is the correct answer. Which of the following compounds is insoluble? All right, well, this goes back to chapter 2. Okay, first you got to learn how to write your inorganic compounds. Then you have to know which ones break up into their charges. Here, you also have to memorize which ones are soluble and not soluble. Potassium. Potassium is a group 1. What did I say about group 1? A lot of people miss these, and these are not problems with calculations. And the reason why that's a problem, calculations take a little bit more energy and time, so you do not want to miss these types of questions. Potassium is group 1. We know that all group 1 cations are always soluble, okay? So let's just see. K1, soluble, okay? You know also ammonium cation, always soluble. There's ammonium, always soluble. Lithium, group 1, always soluble. Now what about the anions that are always soluble? Remember the nitrate. Nitrate is always soluble. So the only answer here is silver chloride. And silver, the chlorides are typically soluble unless they're with, one of them is silver, remember, or lead. They're with lead, or they're with silver, or they are with mercury. They are going to be insoluble. I'm going to go with this word here. You need to memorize and apply. But if you don't have anything memorized, you're not applying. So that leaves you helpless in the exam. And the only thing you'll be able to do is guess. Okay? And the probability when you have 5 options is a 20%. So if you got a 20 to 40% on this exam, it's probably because you're guessing, because you have not done the work to memorize and then practice applying. All right, let's go with number 5. Which of the following is not a strong acid? Once again, we have to memorize and apply. So we have to memorize our 7 strong acids. So let's memorize them. Sulfuric acid, strong acid, HCl, HI, HBr. There's 7. Perchloric acid, so chlorate, Remember I said clam, that's ClO3, and that's a 1 minus, so that's chloric acid, and then perchloric acid would be HClO4. So that's 1, 2, 3, 4, 5, 6, and then nitric acid. Okay, which comes from nitric acid, comes from nitrate, and there you go. So the US acids are weak acids. So HI is a weak acid. Okay, you see the sulfuric acid there. You see nitrous acid. Oh, HI is a strong acid. See, this is the application here. That's a strong acid. So this is strong acid. Nitrous, the US acids are weak. Okay. HCl is a strong one. And phosphoric acid is a weak acid. So it's phosphorus acid and nitrous acid. Memorization and application. What is the oxidation number for nitrogen? And so remember that when we made this correction in class, it should be sulfur and sodium sulfate. So let's look at this. I showed you that you need to, I like how the book does it. They do these circles for each one of these elements, and then they do the boxes. And so inside here, oxygen, and these are your memorized rules. Okay, remember the memorized rules that I showed in class? Oxygen does a -2, and I said most always. And then sodium is always a +1. Why? Because it's group 1. Now you see that there's 2 of them. So 2 times a +1, it would be a +2 in the box. And there's 4 oxygen, so 4 times -2 is a -8. All right, this has to sum to the overall charge, which in this compound is 0. So if you have there's only 1 sulfur, you have a -8 +2, this means a +6 would give you a 0. And since there's only 1, it's a +6. So the answer is 6. If you haven't memorized some of these rules and practice applying, once again, you're left guessing. You have a 20% chance of getting that one correct when you're guessing. All right, question number 7. How much energy in joules is contained in 1 mole of 552 nanometers of photons? We worked a quiz question on this. You have to know the formula E equals H nu, and you're given a wavelength. So nanometer, you need to know wavelength is nanometers, 552 nanometers. We have to solve for nu. So C equals lambda nu. So we can solve for nu by going C divided by the wavelength. And we've talked about C being 2.9979 times 10 to the 8th meters per second. We see that we have meters here, and we have nanometers. So we're going to have to convert the 552 nanometers into meters. And so we do some dimensional analysis here, and we get 1, 2, 3, 4, 5, 6, 552 meters. And then so we can divide this number, and then that should give us a frequency of 5.4309783 times 10 to the 14 reciprocal centimeters. And now we can plug it into find the energy. Planck's constant, you have that on your periodic table. That is 6.626 times 10 to the -34 joules times second. And then so when you do your energy here, I don't know what just happened there. Okay, so then you just do energy equals, you take this frequency and you times it by Planck's constant, 6.626 times 10 to the -34 joules second, and you get this number here, C. Wait, it's not C on this one. On this one, your answer is A. So question B, it's 3.60 times 10 to the negative 19 joules. Okay, so now let's go to 8. What is the molarity of a solution? So molarity is moles of solute over 1 liter of solution. We memorized that. Okay, we have 3.554 grams of magnesium chloride. And we have dissolved in 120 milliliters of solution. So we've got to convert grams to moles. So what is the molar mass? Magnesium, if I look at the periodic table, I see it's 24.3050 grams per mole. And the chlorine, we have 2 chlorines, so now it's 2 times 35.4527. You add that up, you should get 95.21 grams of magnesium chloride for 1 mole of magnesium chloride. So then you do 95.21 grams for 1 mole of magnesium chloride. And that should give you 0.0373 moles. You also need to convert 120 milliliters into liters. So 1,000 milliliters into 1 liter, which is 0.120 liter. And now you can just put it in that formula where M equals 0.0373 mole divided by 0.120 liter. And that should work out to be answer B, 0.3100 molar solution. Okay, I'm going to erase all of this so we can have some white space. Next question. How many, okay, this is an important one, moles of sodium ions? Well, there you go. You're going to need some conversion factors. You have, this is your given. Remember I told you anytime you see 25.6 molar big M, it's mole, in this case, mole of sodium sulfate equals 1 liter of solution. I said one day that you need to always make that a conversion factor. Okay, so it's asking how many moles of sodium ions. So this breaks up into 2 sodium ions plus 1 sulfate ion. Okay, so there's your ion. So they want to know how many moles of sodium ions. So you're given 150 milliliters, and there's 1,000 milliliters for 1 liter. And then you're going to use this conversion factor. For 1 liter, you have 25.6 mole, but that's of sodium sulfate. For 1 mole of sodium sulfate, you have 2 moles of sodium ion. And then when you do that math, you see that the answer is 7.68 mole. Okay, so number 10, how many grams of solute are present in 25 milliliters of 0.75 molar solution of aluminum nitrate? Once again, you see the big M, make it a conversion factor, 0.75 mole of aluminum nitrate equals 1 liter solution. How many grams? Well, this will give us moles. We'll have to convert 25 milliliters into liters, but we also need the molar mass. I think some people are still having trouble understanding how to convert molar mass. So do you see that this is 1 aluminum? Do you see that this is 3 nitrogen? And this is 9 oxygen. So if you take 1 times 26.98, 3 times 14.01, and 9 times 16.00, and you add all that up, you should get a sum of 213.01 gram per mole. Now you can go 25.0 milliliter, 1,000 milliliters for 1 liter, and then you're going to do this 1 liter, 0.75 mole of aluminum nitrate, but that gives us moles, and then you're going to do the molar mass. For 1 mole, you get 213.01 gram, and then that should be 7.68. Oh, no, this is number 10. It should be 3.99 grams. Okay. Let's do the next one. Which orbital is the s orbital? So S is the L are the shapes, the quantum number, and L equals 0 is the S shape and its sphere. Some people had which one is the P shape. Well, L equals 1 is P shape, and you have this and this and this. So this is the P shaped. Okay, so that would be P shaped. Once again, it is memorization. Okay, so if you chose B and C, you were choosing the D shape. And I'm going to stress it again. If you do not memorize and practice applying, you are guessing. And guessing, you're getting 20 to 30 to 40%. So if you're getting that score, then you're not memorizing and applying. All right, what is the final concentration of 12.5 milliliters of 6.50 molar sulfuric acid diluted? So this is the M1V1 equals M2V2. And you have what is the final concentration. So what is V2? And so you have to define your variables. So what is the final concentration, not concentration, would be M2. So what is M2? So then you're going to solve M1 V1 over V2. Okay? And then you want to define your variable. So it's asking for what's the final concentration. And so V1 is 12.5 milliliters, and M1 is 6.50 molar solution. Diluted V2 is 25.0 milliliters. All right, so now you want to solve. So 6.50 molar, V1 is 12.5 milliliters divided by 25.0 milliliters. And so when you solve that, you should get 3.25, which is A, molar solution. Okay, number 13, it's asking about heat, and you have a block of copper, so this is the Q equals ms delta T, and you have a mass of 3.25 grams. Most people got this one. And you have to figure out your delta T, T final minus T initial. All right, so then you want to figure out what your delta T is. So from 2, so 2 is final, initial, so you got a negative 11.5 degrees Celsius minus, because it's a negative 35.6 degrees Celsius. So that should be delta T. Remember, when you have a minus minus, you plus it. So that's a 24.1 degrees Celsius. And then specific heat of copper is given to you. So Q equals 3.25 grams times 0.385 joules per gram degrees Celsius times 24.1 degrees Celsius. When you multiply that, most people got the correct answer of 30.2 joules. Once again, you memorized the formula and you practiced applying. So if you got that right, that's what you did. And you need to do that with every one of the concepts. All right, so going on to the next page, which element belongs to the D block within the periodic table? So I told you got to work on electron configuration and you need to learn which ones are the D block. Hopefully you know that the S block, it looks like that. Hopefully you know that's the D block. Hopefully you know this is the P block. And then you have your F block down here. So any elements that you would find in this area is the D block. Some people had, I think, on the other one, the P block. So that would be elements here. So this is potassium is S block, magnesium is S block, silver is D block, the C is the F block, and the bromine is the P block. So you do have to memorize that. How much heat is produced by the complete reaction of 5.56 kilograms of nitromethane in the following reaction? And then it gives you the formula weight of nitromethane. So that saves you time, right? 77.05 grams equals 1 mole. This is that area where I told you you're going to have to use this delta H as a conversion factor. So this is your given. You're starting with 5.56 kilograms of nitromethane, and then for 1 kilogram you get 1,000 grams, and then you got to go from 77.05 grams of nitromethane for 1 mole of nitromethane. That's CH3NO2. And then the other conversion you need is negative 1418 kilojoules equals, and where is the nitromethane? Right here. And what's the number in front of it? 2. For 2 moles of nitromethane. So then you do for 2 moles of CH3NO2, you have 1418 kilojoules of energy. And so then when you multiply, divide, and multiply, and then divide by 2, your answer is 5.12 times 10 to the 4th kilojoules. All right, number 16. Choose the correct electron configuration for silicon. Silicon is element number 16, so you can add up. There's no charge there, so which ones even have 16 electrons here? So here, 1, 2, 1, there are 2, and 4, and 10. 10, that's 16 electrons here. 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. Here you have 14 electrons. Here you have 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 20 electrons. So you could have done it that way. And then you should know that when you do the Alboff building up principle, you go 1s2, 2s2, 2p6, and then if you notice silica is on the third row, so you go 3s2, and then you get to 3p4. So A is the correct answer. And that might have been different for the other exam. Okay, use the standard enthalpies of formation to determine the delta H. This is the place where you do the summation of your H enthalpies of product minus the summation of your enthalpies of reactants. And so you have your reaction. Now, some people said, oh, it wasn't given to us. Okay, if it is a solid and an element in its elemental state, you're supposed to know that's 0. Okay? And so if you look, every other one was provided on that sheet. What a lot of people did, so if you didn't get products first, you would have gotten the wrong answer. So the products here would be 3 times, and if you look up the CO2, you see that's negative 393.509. Okay, so you have to multiply that out, and that works out to be negative 1080.527 kilojoules. And then you want to subtract the reactant side, And here, see, you have your coefficients here. So this one here is just 1, which would be negative 824.2. And then you add this with 3 times the carbon monoxide, which is a negative 110.52. Okay, and so when you have a minus and then this is a minus, this ends up being minus a total of negative 1155.7 kilojoules per mole. When you have the minus and the minus, that ends up being a plus, right? And so your answer ends up being a negative 24.8 kilojoules. So that's an exothermic reaction. So that's applying the formula, but you also have to know the rule. You had to memorize the rule that if your element is in the standard state, the delta H of formation is 0. And then the other compounds, you have to look at the chart that I gave you and multiply them by the coefficient. All right, so now we are on number 18. Which of the following is isoelectronic? That means the same electron configuration as O2. So I like to look at my periodic table and I see oxygen and I see 2 electrons. So if you add 2 electrons, because electron configuration is the address of the electron, it's about the electron. So you move 2 electrons, you move forward, you see that that's neon. And so here's neon. But it says choose all that apply. So if I go on through there, I'm going to see that's 1s2, 2s2. Oxygen then would be 2p4, but O2 minus, you're going to have to add the 2 electrons. So then you're going to go 1s2, 2s2, 2p6. And that option is A. So A and C are both correct options. All right, so now we're on number 19. How many milliliters sulfuric acid neutralize so many mils of a molar solution of potassium hydroxide? I told you the first time you get these acid-base reactions, you need to write a balanced equation. And I only saw maybe 1 or 2 people actually do this. Okay, so a lot of people got this wrong, and you're going to see it again. Sulfuric acid plus KOH, I think I even worked this on the board, that becomes K2SO4, and these are all aqueous, 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 plus water. Now the reason why this is important is because you have to balance it. So here you have 2 potassiums. Once again, do you know that that's a sulfate is 2 minus, so you need 2 of the potassium pluses. This is chapter 2. So if you did not learn chapter 2, you're not going to be able to write a balanced equation. Okay, so that's the problem, is chapter 2. Now we need to write the balanced equation so we can get this ratio. 1 mole of sulfuric acid equals 2 moles of potassium hydroxide. We need that conversion factor. I also said to you, anytime you see this big M, write it out as a conversion factor. So 1.28 mole of sulfuric acid equals 1 liter. And then we also see this here, 0.427 mole of KOH equals 1 liter of solution. Now, this is a conversion factor. These coefficients are conversion factors, and this is a conversion factor. So our only given, meaning a number with a unit, is 60.2 milliliters, and it is of the KOH solution. So this is KOH, and so then we can go to 1,000 milliliters of KOH for 1 liter, and then we can get into this conversion factor. 1 liter of KOH equals 0.427 moles of KOH. That's not what we want, is it? It wants how many milliliters of sulfuric acid. So how do we go on dimensional analysis from KOH to sulfuric acid? we only know one way, and that's this mole to mole bridge. So we have to have those balanced coefficients. And so now we know 2 moles of KOH equals 1 mole of sulfuric acid. And it doesn't ask us for how many moles, it asks us for how many milliliters. So then we use this other conversion factor, which is 1.28 moles of sulfuric acid for 1 liter. And then it wants milliliters, so 1 liter equals 1,000 milliliters. And then you do all of that math, and you should have come up with 10 milliliters. If you came up with 20, you did not write your balanced equation to get this ratio. If you applied M1V1 equals M2V2, which is wrong, okay, and you do that in Chem 2, you're not going to get any credit whatsoever. That will work if it's a 1-to-1 molar ratio, but this is a 2-to-1. You have to write your balanced equation. How do you know when to do M1V1 equals M2V2? When you have the same substance. But in this case, you have sulfuric acid and potassium hydroxide. Those are two different substances, and that's when you know I need to write a balanced equation, and I need to use these dimensional analysis. Okay? All right, what is the electron configuration for zinc 2 plus? Okay, well, let's figure out what zinc is. So let's write for zinc. So I go and I find zinc on the periodic table, and I'm just going to go and do, okay, we got 1s2, 2s2, 2p6. Now I'm on the third row, 3s2, 3p6. Okay, I'm at argon, and then I'm at 4s2, and then I got to go 3d, and now I'm going to count till I get to zinc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 10. Now, what I wanted you to pay attention if you read your book, that when you take these 2 electrons, you take them from the higher number. You take them from the 4s2. You would take those 2 electrons from there. So then this would end up being, you could do 4s0, 3d10. But, so which would be there, which is D. This doesn't even exist, but a lot of people did this one, okay, and I accepted both of them, okay, so either one was okay. All right, that is the end of your multiple choice questions. Now you have your open response questions. Okay, so in your open response questions, this is Hess's law. I told you would have Hess's law. You come here and you see that this is your carbon. You say carbon's on the correct side. Yes, that's good, but it needs a 5. So we're going to rewrite it. 5 carbon plus 5 oxygen goes to 5 CO2. And then you're going to have to take that delta H, negative 393.5 kilojoules times 5. Okay, so you rewrote that. All right, now we can go to the hydrogen. So here we have hydrogen. We found hydrogen. It's on the correct side. It's on the reactant side, but this has a 6. So we need to do all right, so now we see that if we multiply this by 3, so if we do multiply everything by 3, we could get the 6. So we're going to do 6 hydrogen plus 6 oxygen goes to, not 6, 3 times that will be 3, and 3 times 2 is 6 water. And then we have to multiply this by 3. So that delta H becomes negative 483.5 times 3. And then we can just do that, right? So we got to go over here, and we see that this one here has the C5H12 on the incorrect side, but it has the right coefficient. So we're going to flip this one. So now we're going to write 5CO2 plus 6 water gas goes to C5H12 plus 8 oxygen. And then when we flip it, we've got to reverse the sign. So delta H equals 3244.8. Now we've got to see, we have this here, which is on the correct side. And we have the 5 carbons on the correct side. And then we have our 6 hydrogens. Now we got to see that these other ones cancel out. So here we have 5, 6, 7, 8 oxygens. You see you have 8 oxygens over here. You have 6 waters that are gas over there. You have 5 CO2s that are over there. So then if you add all this up, you would see that these add up to the same thing. And so when you add all these up, you also add up all your delta H's. And so if you take negative 393 times 5, that times 3, and you add all of these up, you should have gotten negative 173.2 kilojoules. All right, the next one, balance the equation below. So you got 1 point for that. So you have 2 sodiums, you need 2 sodiums here, you have 2 nitrates, you have 2 nitrates, you have 1 copper, and you have 1 sulfur. Okay, so that's worth a point. Calculate how many moles of sodium nitrate. Okay, so we want to know how many moles of this, and we want moles produced when we have 4.76 grams of sodium sulfide reacts with 3.50 grams of copper nitrate. And then we also have the formula masses for sodium nitrate is 85.01 gram per mole. Sodium sulfide is 78.07, and copper nitrate is 173.56. Okay, so we have all the information. You have to figure out, since we're given both amounts, this is a limiting reactant problem, and so we're going to have to convert the grams of each to mole of the product, sodium nitrate. So you should take 4.76 grams, and then you would do 78.07 grams for 1 mole of sodium sulfide, and then for 1 mole of sodium sulfide, you get 2 moles of product. Okay, and we'll just call this P. And that works out to be 0.1219 mole of sodium nitrate, which is the product. And then you want to do the same thing with this one. 3.50 gram of the copper nitrate. And then you use your formula mass, 173.56 grams for 1 mole. And then for 1 mole of copper nitrate, we look at the coefficients, we have 2 moles of product. And then when you do that math, you see that that's 0.0403 mole of sodium nitrate. Well, which one's the least? This is your least, so this is your limiting reactant, and this is also the amount of moles that is produced. So that's your answer. All right, the next problem, not that many people seem to do this one. You have to assign oxidation states on each element, okay? I went ahead and gave people credit, but it wasn't right. So if you have magnesium in a compound, it's a +2, okay? And then over here by itself, magnesium goes to 0 because that's one of the rules. When an element is in its natural state, its oxidation number is 0. And then chloride is a -1. It's not a -2. There's 2 of them. The oxidation number is -2. And over here it is 0 because it's in its natural state. Now you're supposed to connect them just like this. If you go from +2 to 0, it is reduction. If you go from -1 to 0, that's an increase, that's oxidation. So the oxidizing agent is the one that goes reduction, and that's magnesium 2+. It's not magnesium. Magnesium solid is not the oxidizing agent. It's always the reactant, okay? And so it's 2+, and it needs to have the plus. The reducing agent here would be Cl1 minus. It's not Cl2. No, it's not the product. Okay, so oxidation, the one that goes oxidation, is the reducing agent. The one that undergoes reduction is the oxidizing agent. Should work on that. Okay, this one, I told you, you have to be able to apply these rules. So here you do your ionic formula. So lead is going to be 2 plus, and you have 2 nitrates. And you're supposed to have every one of these phases or it's wrong. So the fact that I gave partial credit on problems that was wrong is kind of disturbing for me, okay? So these break up into their ions. These are strong electrolytes. Now you do, see lead here is with nitrates. Now lead's going to be with the sulfide. You always put the electropositive, the cation first. And since this is 2 plus and this is 2 minus, then that would be a sum of 0. If you do the 2 and the 2, it still is going to cancel out. You have to have lowest terms. And then the other one here, sodium with nitrate, sodium's a +1 nitrate, so it's just NO3. And you should know that those are aqueous. Anytime you have group 1, always soluble, nitrate always soluble. And another thing, now you're supposed to balance this, right? So this should be a big 2. A lot of people didn't balance. All right, so here when you do this, you write the PBS is a solid because of your solubility rules, but those are insoluble, and then you would have to write these is 2 sodium plus 2 nitrate. And then your net ionic is just the lead and the sulfur that go to lead sulfide, okay? So that's your net ionic. And these other ones are on both sides of the equation, so they're considered spectator. Draw the orbital diagram for the following elements. Okay, so you look at your periodic table and you see aluminum is 1s2, 2s2, 2p6, but it's not 2p6, is it? Yeah, it is 2p6. And then 3s2, and then 3p1. And then so you have 1 s orbital. For p, you have 3, so we're going to do 3 boxes. You have 1 orbital, and then here you have 3, and then you put your electrons in. Here we have 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, aluminum is number 13 element, so that means it has 13 electrons, and that would be the orbital diagram. Okay, nickel. Well, let's first see what nickel looks like. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then when we're in the transition, it goes 3d, and we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons. It's number 28, but see it has a +1, so we're going to have to subtract an electron, and that's going to be 7. Now you draw your orbital boxes. For S, you're only going to have 1. For P, you're going to have 3 boxes. S, you're going to have 1. P, you're going to have 3 boxes. S, you're going to have 1. D, you're going to have 5 boxes because you have 5 orbitals. 1, 2, 3, 4, 5. Now you fill in your electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and we need 27, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so you see that you have 5, 6, you have 7 electrons here. And what I wanted to see is that you followed the Hund's rule, where you fill up the half degenerate d orbitals before then you put the electron in the other. Okay, that sums up our exam 2. Make sure you understand how to work those for the future.